Let's take a look at fusion and stars. So fusion is the act of combining nuclei into a larger nucleus and releasing energy in the process. So an example of a fusion reaction would be hydrogen 2 and hydrogen 3 coming together to form helium 4 and an extra neutron. Another example would be 3 heliums coming together and fusing into a carbon-12 nucleus. You could also have 2 carbons fusing together to form magnesium-24. Each of these reactions is a fusion reaction, and each of these reactions would release energy. If we were to look at the mass defect, the mass of the reactants on the left side would be greater than the mass of the products over here on the right side. There would be a decrease in the mass, a mass defect associated with this reaction, and that mass defect would be associated with the amount of energy released. And just like in the past, the connection between the mass defect and the energy released is found through E = mc squared. So for any of these fusion reactions to happen, the nuclei must combine. And in order for that to happen, those nuclei have to come together and overcome the Coulomb repulsion. They have to overcome the electric repulsion because all nuclei are positively charged, so we have to bring together 2 positively charged objects. That's not easy to do, but the conditions are favorable for fusion to happen if we have a high temperature. Because if we have a high temperature, then the nuclei may have enough kinetic energy to approach each other and undergo a fusion process. Now, conditions are favorable also if we have a high pressure. And that's because if we have a high pressure, then the nuclei are all relatively close to each other. There's many opportunities then for a fusion reaction to occur. So one location where we tend to have a very high temperature and a very high pressure is inside of the cores of stars. So let's think about stars. Stars are huge balls of mostly hydrogen, or they're objects which once were huge balls of hydrogen. We'll talk about that a little bit later. The mass of a star can range from about 10 to the 29 kilograms to 10 to the 32 kilograms, which is about 1/10 the mass of the Sun to 100 times the mass of the Sun. And here I'm using this symbol M with a little circle dot. The circle dot refers to the Sun. So M with a little circle dot next to it refers to one mass of the Sun, or a solar mass. And we've seen this before. We saw a solar luminosity, and we can also talk about a solar radius, the radius of the Sun. And these are commonly used when talking about other stars. So why hydrogen? Why would stars mostly be made of hydrogen? Well, that's because after the Big Bang occurred, matter mostly formed the simplest element possible, which is hydrogen. Now, there was a very small amount of helium formed and lithium formed, but by far the most common element formed after the Big Bang was hydrogen. And that's still the case. Most of the matter in the universe is hydrogen, and so stars are mostly hydrogen. Although they can have trace amounts of other elements like helium, lithium, calcium, oxygen, carbon, iron, and so on and so on. So how do stars form? Well, it starts with a large interstellar cloud of gas, usually called a nebula. And this cloud of gas, perhaps a disturbance occurs, but it collapses due to its own gravity. So the gravitational force will cause a gas cloud to collapse. As it collapses, it loses gravitational potential energy, and the gravitational potential energy is converted into kinetic energy of the molecules. In other words, as it collapses, its temperature increases. So the collapse continues until we have a center with a very high density and a very high temperature. And there's little bits that are left outside. Those are the things that form planets, moons, asteroids, and comets. But the majority of the mass tends to move toward the center. This is what forms the star. And at the center of the star, the core, the temperature and the density are very, very high. And eventually they become high enough for fusion to occur, for those hydrogen atoms to fuse. Once fusion begins to occur in the core, there is now an outward force. So there's an inward force of gravitation pulling everything together. But once the core is undergoing fusion, there is an outward force from that fusion. We will refer to this outward force as radiation pressure. It's also caused by gas pressure, but we'll just talk about radiation pressure. And the balance between the inward gravitational force and the outward radiation pressure from fusion is called hydrostatic equilibrium. So now let's think about three stars with different masses. Let's have a low mass star, a medium mass star, and a high mass star. The low mass star will have a relatively low temperature and pressure in the core. It's still high by Earth standards, but compared to other stars, if it's a low mass star, it's going to have a lower temperature and pressure inside of the core. Well, if there's a lower temperature and pressure inside of the core, then we would expect a lower fusion rate. It's not going to be fusing those hydrogens together as quickly. And if it's not fusing the hydrogen as quickly, then that means that it's not going to have as great an energy output as the larger mass stars, which means it's going to have a relatively low luminosity. We would also expect it to be physically smaller because it has a lower mass, and so it's going to have a smaller surface area. And also because its energy output is less, we'd expect the surface temperature to be lower. Now let's go over to the high mass star. We'd expect it to have a very high temperature and pressure in the core, which means it's going to have a very high fusion rate in the core, which means it's going to have a high release of energy in the core, which means it's going to have a very high luminosity. We'd expect it to have a larger surface area because it's physically larger, and we'd also expect it to have a higher surface temperature because it's got a higher energy release rate. What that means is that over here with the low mass star, it's got a low surface temperature. If we apply Wien's law, we would expect the wavelength of maximum emission to be greater because it has a lower temperature. And in fact, most of these very low mass stars have a wavelength of maximum emission that's around the color red or even in the infrared. So these stars tend to look more reddish. If we think about the high mass star, it has a high surface temperature, and by Wien's law we would expect it to have a smaller wavelength of maximum emission. And in fact, for these stars, the wavelength of maximum emission tends to be near the blue part of the spectrum or even in the ultraviolet. So these stars tend to look blue or white. In the middle, all of the values are kind of between the low and high mass stars, and there we'd expect the wavelength of maximum emission to be right in the middle of the visible spectrum, and the star tends to look yellowish or yellow-white, just like our sun. Now it turns out that there is a relationship between the luminosity and the mass of a star. The luminosity of a star is proportional to the mass of a star to the 3.5 power, approximately. What that means is that if a star has twice the mass of the sun, then we would expect its luminosity to be about 2 to the 3.5 times the luminosity of the sun. In other words, about 11 times the luminosity of the sun. So that means its fusion rate has to be about 11 times as great, and so it's going to use up its hydrogen fuel much faster. So yeah, it has 11 times the fusion rate, but only twice the mass of the sun. So it's going to use up its fuel much more quickly than the sun would. Likewise, if we think about a star that has only 1/10 the mass of the sun, then its luminosity would be about 0.1 to the 3.5 or 0.0003 times the luminosity of the sun. And so it's going to use its hydrogen fuel at a much lower rate than the sun. And so this star will be able to use its hydrogen much, much, much longer. So the hydrogen fuel of low mass stars lasts much, much longer than the hydrogen fuel in the high mass stars. Low mass stars have much longer lifetimes than high mass stars. Now, all of the stars that we're talking about, which are fusing hydrogen in their cores, are said to be on the main sequence. The main sequence is a long and mostly stable phase of a star's existence. And the name of this main sequence comes from a graph which was developed by observations of stars in the 19th and early 20th century. And this graph is called the HR diagram. HR for Hertzsprung and Russell, two scientists who developed it or helped to develop it. And I'm going to draw an example of an HR diagram. On the vertical axis, we're going to have luminosity, and not just luminosity, but actually a logarithmic scale of luminosity. And on the horizontal axis, we're going to have temperature, also a logarithmic scale. But what's weird about this is the temperature is going to increase to the left. If you don't like that, it's because of historical reasons, and it's too late to change it, so you just got to deal with it. If we have this graph, the main sequence of stars would be right along this line. Sometimes it's a straight line if we're doing an approximation. In reality, it's more of a curved line like this. And it's also not a strict line. It's more of a region. It varies with different properties of the star. But the sun would exist about right here. And if we were to think about higher mass stars, well, higher mass stars have a much greater luminosity, and they also have a higher surface temperature. So higher mass stars would be in this region of the main sequence. Lower mass stars would have a lower luminosity and have a lower surface temperature, so they'd be over here. So this temperature axis also kind of serves as a color axis, going from red over here on the right, and then through orange, yellow, over to blue, and blue-white. Most of the stars in the night sky that we see are on the main sequence, but not all of them. And next time we'll discuss those that are not on the main sequence.